Hey Raiders, welcome back. Dr. Mitt here. Just wanted to go through the topographic map principles. We've talked about these in class. You read about them. You saw the terms defined in your textbook. You copied those principles from the textbook. We reviewed those in class today. And so now I want to actually just do a quick video recap of these principles, key things to keep in mind as we look at, as we work with, as we interpret topographic maps. So topographic maps is what I'll write on the board here. Topographic maps. Some people call these contour maps because, of course, they're covered by these curved lines that are everywhere, contours, and we'll talk more about that in a second. But we're talking about topographic maps. And again, just a reminder that this root word, topos, is from Greek, and it means place. So a topographic map is a representation of place. And again, just as a reminder, what a topographic map does for us, even though it's in 2 dimensions, it allows us to understand the 3rd dimension. What's the land surface doing? Is it going sloping downward? Is it a slope upward, depending upon the direction of movement? Is this a valley? Is this a mountain? Is this a ridge? And all of those sorts of things we can understand from topographic maps that we use, whether they're small things that we use in exercises or whether it's a full-size topographic map of the Huntsville quadrangle or something. And we'll be looking at those maps soon together. So the topographic map, a key thing, again, since these are sometimes called contour maps, is to define the word contour. A contour is a line on this type of map that connects points of equal elevation. Connects points, a line that connects points of equal elevation. Anywhere you go on a particular contour, it will be the same elevation. That's the whole idea of what a contour is. It is a line that connects points of equal elevation. Remember that for elevation, our datum, the thing that we measure against, all of our measurements are against a particular datum or using a particular datum, is mean sea level. And again, it must be a mean because sea level is changing just with tides and with storms and that sort of thing. So we have mean sea level, and we always report our values as AMSL, or above mean sea level. Please remember that. You'll see that on a future assessment. So we also need to know what a contour interval is. Contour interval is the difference in elevation between 2 adjacent contours. Adjacent just means those that are next to each other. 2 adjacent contours. And so as we talked in class today, you can find on the corner of a map somewhere, it will tell you what the contour interval is. You can also determine it by looking at 2 index contours that are close together and just kind of doing the math and say, oh, these contours must be spaced this much apart. They're that different in their elevation. So a contour interval, write this just a little more clearly. Contour interval is the difference in elevation between 2 adjacent contours. We also, you'll recall, have what are called index contours. These are bold, means they're darker than the other lines, the other contours. They're bold. Usually, on many maps, usually 5 contours apart. along which the elevation is labeled. So if you want to know what an elevation is, because not all of the contours are labeled, some of the contours, if all of the contours were labeled, we'd have a map that's just covered with numbers, and it'd be hard to really make much sense of it. So what they do is they just make every fifth contour, in most cases, every fifth contour is bold, and somewhere along that line, you will see the elevation labeled for you. So we have contour, line, a line that connects points of equal elevation. We have a contour interval, the difference in elevation between two adjacent contours, and index contours. These are bold, usually 5 contours apart, along which the elevation is labeled. It's not always convenient for you to see where it's labeled, but somewhere along that contour, if you trace it around a hill or around a valley, you'll be able to find the index contour. If it's bold, somewhere you'll be able to find the elevation. It'll be labeled for you. A couple of other key things is that contours never cross. You can't have 2 elevations at the same point. Now, there's one exception. As we spoke in class, you can have a situation at a vertical cliff. If you had a cliff that's completely vertical, you could have contours that are one right on top of the other. Because looking from space, that point on Earth's surface would be a straight line down, right? You'd have that cliff face. And so you could have contours that are right on top of one another if you were at a vertical cliff face. Otherwise, that will not happen, okay? And contours just will not cross because you can't have 2 different elevations at the same point. So contours never cross. Remember, too, that closely spaced contours indicate steeper slope, whereas widely spaced contours indicate I'll just call it a flatter slope, or a more gradual slope. So if you look at a map and you see lots of contours close together, that's really steep. If they're stretched out a little bit more, spread out a little bit more, that means that it's a more gradual slope. It's a flatter sort of an area. Remember also that the V's, they're not always perfect V's, but these V kind of shapes, V's in contours point upslope or upstream. So if you see those V's, we understand that those V's are indicating the upslope direction. So if you had a stream, if you had a river there, they would be going the opposite of the V's. So the V's in contours point upslope or upstream. The final thing that I want to point out is we have what are called hatchered contours. We have these little tick marks that point inward, hatchered contours. These indicate a closed depression. A closed depression, a low spot. And again, we could see this sort of a feature if we had a sinkhole. We could see this sort of feature if we had a crater, like at the top of a volcano. Or we could see this if we had an impact structure, for instance, where a space rock had plowed into the Earth's surface. And, we might produce rims and we might produce rays and all that, but we would have this depression, and it would be shown with Hatchard contours if it had this sort of closed depression sort of shape. So these are the basic principles, the basic rules of using topographic maps. We'll get more and more chances to practice at contouring, not only at contouring, but making sense. When you look at a topographic map, can you understand what it's showing you? And we'll move in the direction of more and more interpretation, and also even trying to make a topographic profile, which is drawing sort of a cross-section using a topographic map that's showing things just in 2 dimensions to actually visualize what that third dimension looks like by kind of doing a cross-section, kind of a cutout. So thanks for listening. This is just a little bit of review of what we've done in class, what you did yesterday in class with the sub, what we're doing in class today, and what we'll be working on over the next several days. Thanks for your attention. Take care. Keep working, Raiders.